In the previous lectures, we have already discussed the Lorentz transformation, and this is for the moving frame x prime equal to this y prime, means we are having the motion along the x-axis. So the prime coordinates are of the moving frame and the unprimed are of the stationary frame. So this was the Lorentz transformation in which gamma is equal to 1 over 1 minus v square over c square. Similarly, we can convert to the stationary frame coordinates by this. The way to remember them is x prime equal gamma x minus vt. So here if I replace x by x prime, then here x will be replaced by x prime and t with t prime, and the sign will be positive. So this way I can do the conversion. There is another way to write the gamma 1 minus v square over c square. So I can define v over c as beta, and we can write the gamma like this as well. Now under Lorentz transformation means what is actually this transformation? This is the transformation between the stationary frame and the moving frame. The problem that Lorentz was facing, it was not the length contraction or time dilation, because the length contraction means the space contraction, and the time dilation, Lorentz has already done this thing. But the problem was of the reference frame, that if light is moving, then this motion is with respect to which frame? This motion is with respect to what? And that was the confusion which was clarified by Albert Einstein, and he said that when the Maxwell equations are not putting any restriction on the reference frame or on the motion of light, then why we are considering or we feel the need of some reference point. So it is something which is without any reference point. This motion is not a relative motion. This is a motion which is independent of any reference. So keeping in view all this thing, we know that S is equal to Vt. And from here I can write that if C is here, then it is S over T. This is space and this is time. The space I can also write is length, and over length over time. Now length is contracted, means it reduces, while time dilates. So how this can be constant then? If, for example, length was shrinking and time was shrinking as well, then C may remain constant. But this one is contracting and this one is dilating, this one is increasing. So then how C can remain constant? And for this, we are compelled to move into more calculations, like we find a certain length such that that length is agreed by both the primed frame and the unprimed frame, by moving frame and the rest frame. Similarly, we should agree on a time such that that time is the same for both, so that when we find such a length and such a time, so it will be the invariance of space and time. Like the length measured, that length which will not be contracted, that time which will not be dilated. So we will have to go for that space and for that time which remains invariant under Lorentz transformation. Just like as we did in chapter 1st of the Griffith's electrodynamics, we did the rotation matrix. Like when we rotate the matrices, The vector should not be dependent on your coordinate system. Like the coordinate system, if you consider this one are at a certain angle, the vector is supposed to be invariant under coordinate system rotation. It's not only vector but all the relations of vector like dot product and cross product or any addition, they are supposed to be invariant under rotation of the coordinate system. They should be the same. Now here is the invariance under Lorentz transformation, or we can say the invariance between the moving and the stationary frames. So we will have to move to the four vectors. We can call it a space. It is four vector space. Like the three vector space are the three dimensions vector space. We already know that in 3D we write any vector r in x, y, and z components. We can write any vector in this form such that x, y, z are actually the coordinates. X, y, and z are the coordinates. Now, this is just space. X is a space, is a length, y is a space and length, and z as well. And the whole combined in a 3D, three-dimensional space. It is having three dimensions. Now, with this space, we will have to combine another one-dimensional space, which is of time, because here we are having x, y, and z, and time is additional. Now we will have to couple it. On one side, we want that space and time. So space-time invariance. Space and time are to be invariant under Lorentz transformation. And on the other side, we are having momentum and energy. So momentum and energy are also supposed to be invariant under Lorentz transformation. When I talk of space and time to be invariant, it means the conclusion of this will be that C will remain constant. And when when momentum and energy will remain invariant, then mass of the system will remain constant. So these are the two things we will have to go behind. Now this is space, and this one is another coordinate of it, but this is time. What we should do here, that if I write this one, the 3D, this is x, y, and z. And this is to be combined with 1D. And 1D is just time. Now this is spatial coordinates, x, y, z. This one is time. These are of the same dimensions. So if I want to make them 4, then I will have to keep their dimensions the same. So how I can keep the dimension the same is it is space and time. So if I multiply this with v, then vt is actually space. And I cannot multiply it with v, any velocity. This should be a velocity for whose constancy I am struggling. And that's why I will multiply it with c. So I will have a 4-vector system, and this will be ct, x, y, and z. Now it can be a 4-vector situation or 4-vector form. Let me call this one x0. Some people do write in the subscript this x0. So it is up to you, whichever notation you like. But I like this notation due to the reason, and Griffiths is also following this one, which we will study in the coming lectures, the covariance and the contravariance. And for that, we will have to go on with this notation. So x0, and let me call this as x1. Now we know that x0 is something which is associated with time. x1 is associated with the x space coordinate. Similarly, x2, x3, and this is now a four-dimensional vector, four-dimensional space. We are now dealing with this one, and now how the Lorentz transformation will look like under this conversion. Let me write x1. Now x1 from here, it will be x1 prime because the prime coordinate is here, and x1 is equal to x is equal to gamma times, and now here it is x, so it will become x1 minus v times t, minus v times t. In this notation, it will be the x prime. I can convert this one, x1 prime is equal to gamma x1 minus. Now I have defined beta equal to v over c, so I can write this as beta ct. For v, I can write beta c and then time. And this I can write is x prime is equal to gamma times x prime. Now what is ct? Minus beta, and ct we have defined is x0. So this is one of the conversion. Similarly, I can write, okay, do differentiate between x1 and its prime. Similarly, I can write y1 is x2 and it will be prime, it is equal to x2, and x3 prime is equal to x3. So I have written the xy and z here, the spatial coordinates, and now the time coordinate will be, take this equation, and this is t prime is equal to gamma times t minus v over c square x. Now convert this one. Let's multiply both sides by c. Then it will become ct prime equal to gamma in ct minus v over c and x. One cc will simplify with this one. Now, if ct is x0, then what about ct prime? It will be x0 prime. So this is x0 and prime is equal to gamma times ct is x0 minus, what about v over c? V over c is beta, and x is equal to x1. So I have converted these into the x0, x1, x2 and x3 forms. And now I can write all this thing in a matrix form. We will start from x0 because this is our first coordinate. Then x1, then x2 and x3. So in a matrix form, I can write is x0, x1, x2, x3, and these are primed. This is multiplied, this is equal to, and now look at the matrix. This should be a 4 by 4 matrix, And look here, x0. x0 is gamma time x0, so it means it is gamma x0. x0 I will write here, x0, then x1, then x2, then x3. So what should be here? The first term will be gamma. Then the second term will be minus gamma beta, and x1 is here, right? So I can write that it is gamma and then minus beta gamma, while the two terms will become 0, 0 here. So it will be x0 prime is equal to gamma times x0 minus beta gamma times x1. So it is this equation. Similarly, the rest of the terms will be for x1. Now it will be gamma times x1. So it will be, means the first term is multiplying with this. So I will have to write this one is with x0 I am having gamma times beta. So the first term will be minus beta and gamma. So minus beta gamma x0, and then this will be gamma, and the other two terms will be equal to 0. Similarly, y prime, this is now x2 prime, is equal to x2 prime. So it should be with this one on the third place. So it will be 0, 0, 1, 0, third place. And the last one will be 0, 0, 0, 1. So this is the matrix representation of the Lorentz transformation under the 4-vector space. Okay. Some books will not call it a space because it is not space. Space means it is this three-dimensional space. So in order not to confuse it with this one, but we can have space of more than 3 dimensions. It is now a generalized term is space. Let me reiterate why we are going behind the 4 vectors. Because we want C to be constant. And in order C to be constant, we should find a length such that length is not contracted between a rest and a moving frame. It is independent of motion. It is to be a length on which both the frames will agree. Because under the Lorentz transformation, length is contracted. So we should go for a length and for a time which is not to be motion dependent, and that will keep the velocity of light, the c, is constant. Then another thing that we are having is the momentum and energy, and the momentum and energy, they are also to be invariant under Lorentz transformation, and that will result in the constancy of mass. So that is our goal, and now I can write this thing in a compact form. Is, you can call it a compact form or abstract form. This is x mu prime is equal to summation on nu equals 0 to 3. It is running from 0 to 3, and lambda. This symbol is lambda, capital lambda, while the one lambda which we use for the wavelength is the small lambda, and it is having a subscript mu and a superscript mu, and x to the power mu. X to the power nu. It is nu. So here, look here. Here are the prime coordinates and here are the unprimed. Nu is running from 0 to 3. So it will be x0, x1, x2, x3. While we are having mu here. So if this is 0 here, then it will be 0 here. If it will be 1 here, it will be 1 here, and so on. So this is the compact form of the Lorentz transformation. The benefit of writing this thing in a compact form is that our motion in the Lorentz transformation is along x-axis. So we can easily convert, we can easily go to any other axis motion like y-axis. One frame is stationary and the other frame is moving along y-axis. The structure of the equation will remain the same, only x and y will change. Or we can go for any other quantity, like for example, here it is the space. We can go for velocity, for acceleration, and then the lambda will become more complex, but the structure of the equation will be the same. So we have already derived such thing in the chapter first of Griffith for the invariance under rotation. There was a rotation matrix that we have derived. We have done there for two components, and then we extended that information to three components.